Hello friends and welcome. Today we shall discuss radial distribution functions, concept of the most probable distances, electronic configurations of atoms and stability of half-filled and completely filled orbitals. Now let us first try to have a look at the main objectives of our today's deliberation. Number first, to give a general idea about radial distribution functions. Number second, we shall be explaining in detail the concept of the most probable distances with special reference to 1s and 2s atomic orbitals. Number third, we shall discuss electronic configurations of the atoms, and finally we shall be discussing stability of half-filled and completely filled orbitals. Now we will start with the introduction about radial distribution functions. In statistical mechanics, the radial distribution function or pair correlation function GR in a system of particles, that is atoms, molecules or colloids, describes how density varies as a function of distance from a reference particle. If a given particle is taken to be at the origin O, and if P is equal to n divided by V is the average number density of particles, then the local time minus average density at a distance r from 0 is P multiplied by GR. This simplified definition holds for a homogeneous and isotropic system. A more general case will be considered as follows. In simplest terms, it is a measure of the probability of finding a particle at a distance of r away from a given reference particle relative to that for an ideal gas. The general algorithm involves determining how many particles are within a distance of r and r plus dr away from a particle. This general theme is depicted to the right, where the red particle is our reference particle and blue particles are those which are within this circular shell dotted in orange. The radial distribution function is usually determined by calculating the distance between all particle pairs and binding them into a histogram. The histogram is then normalized with respect to an ideal gas, where particle histograms are completely uncorrelated. For 3 dimensions, this normalization is the number density of the system multiplied by the volume of the spherical shell, which mathematically can be expressed as GRL is equal to 4 pi r square p dr, where p is the number density. Given a potential energy function, the radial distribution function can be computed either via computer simulation methods like the Monte Carlo method or via the Ornstein-Zernike equation using approximative closure relations like the Perkus-Yavik approximation or the hypernetted chain theory. It can also be determined experimentally by radiation scattering techniques or by direct visualization for large enough, that is micrometer sized particles, via traditional or confocal microscopy. The radial distribution function is of fundamental importance, since it can be used using the Kirkwood-Buff solution theory to link the macroscopic details to macroscopic properties. Moreover, by the reversion of the Kirkwood-Buff theory, it is possible to attain the macroscopic details of the radial distribution function from the macroscopic properties. Plots of the radial distribution functions for the 1s, 2s and 3s orbitals of the hydrogen atoms are shown in the figure. It should be noted that as the principal quantum number increases, the maximum in the probability density occurs at larger distances for orbitals of the same angular momentum type. For example, the maximum probability for the 1s orbital occurs at 1 Bohr, that is 0.529 angstroms. For the 2s orbital, the primary maximum occurs at 5.3 Bohr, and for the 3s orbital, the primary maximum occurs at about 13 Bohr. Similar trends are observed as the principal quantum number increases for the higher angular momentum orbitals, for example, p-type, d-type or f-type orbitals. For example, plots of the radial distribution functions for the 2p and 3p orbitals are shown in the figure. In contrast, if the principal quantum number is held fixed and the angular momentum type of the orbital is varied, we see from the example in the figure that the position of the primary maximum in the probability distribution decreases as the angular momentum increases. Now that we have understood the radial distribution functions, let us now try to learn about the concept of most probable distances. The Bohr radius is a physical constant approximately equal to the most probable distance between the proton and electron in a hydrogen atom in its ground state. It is named after Niels Bohr due to its role in the Bohr model of an atom. Its value is 5.291 multiplied by 10 raised power minus 11 meter. In SI units, the Bohr radius is A0 is equal to 4 pi epsilon naught multiplied by h cross square divided by m to the base e square is equal to h cross divided by m to the base e c alpha, where A0 is the Bohr radius, epsilon naught is the permittivity of free space, h cross is the reduced Planck's constant, me is the electron rest mass, E is the elementary charge, c is the speed of light in vacuum, and alpha is the fine structure constant. In Gaussian units, the Bohr radius is simply A0 is equal to h cross square divided by m to the base e multiplied by e square. In the Bohr model of the structure of an atom put forward by Niels Bohr in 1913, electrons orbit a central nucleus. The model says that the electrons orbit only at certain distances from the nucleus depending on their energy. In the simplest atom hydrogen, a single electron orbits the nucleus and its smallest possible orbit with lowest energy has an orbital radius almost equal to the Bohr radius. It is not exactly the Bohr radius due to the reduced mass effect. They differ by about 0.1%. Although the Bohr model is no longer in use, the Bohr radius remains very useful in atomic physics calculations due in part to its simple relationship with other fundamental constants. For example, it is the unit of length in atomic units. An important distinction is that the Bohr radius describes the most probable radial distance of the electron, not its expected radial distance. The expected radial distance is actually 1.5 times the Bohr radius as a result of the long tail of the radial wave function. Now, let us discuss the next part of our today's lecture, that is the electronic configurations of atoms. In atomic physics and quantum chemistry, the electron configuration is the distribution of electrons of an atom or an atomic or molecular orbitals. For example, the electron configuration of the neon atom is 1s2, 2s2, 2p6. Electronic configurations describe electrons as each moving independently in an orbital in an average field created by all other orbitals. Mathematically, configurations are described by Slater determinants or configuration state functions. According to the laws of quantum mechanics, for systems with only one electron, an energy is associated with each electron configuration, and upon certain conditions, electrons are able to move from one configuration to another by the emission or absorption of a quantum of energy in the form of a photon. Knowledge of the electron configuration of different atoms is useful in understanding the structure of the periodic table of elements. This is also useful for describing the chemical bonds that hold atoms together. In bulk materials, this same idea helps us explain the peculiar properties of lasers and semiconductors. Electron configuration was first conceived of under the Bohr model of the atom, and it is still common to speak of shells and subshells despite the advances in understanding of the quantum mechanical nature of electrons. An electron shell is the set of allowed states that share the same principal quantum number n that electrons may occupy. An atom's nth electron shell can accommodate 2n2 electrons. For example, the first shell can accommodate 2 electrons, the second shell can accommodate 8 electrons, and the third shell can accommodate 18 electrons. The factor of 2 arises because the allowed states are doubled due to electron spin, that is, each atomic orbital admits up to two otherwise identical electrons with opposite spin, one with a spin plus 1 divided by 2 and one with a spin minus 1 divided by 2. A subshell is the set of states defined by the common azimuthal quantum number L within a shell. The values L is equal to 0, 1, 2, 3 correspond to the S, P, D and F labels respectively. The maximum number of electrons that can be placed in a subshell is given by 2 multiplied by 2L plus 1. This gives 2 electrons in an S subshell, 6 electrons in a P subshell, 10 electrons in a D subshell and 14 electrons in an F subshell. The numbers of electrons that can occupy each shell and each subshell arise from the equations of quantum mechanics, in particular the Pauli exclusion principle, which states that no two electrons in the same atom can have the same values of the 4 quantum numbers. Physicists and chemists use a standard notation to indicate the electron configurations of atoms and molecules. For atoms, the notation consists of a sequence of atomic orbital labels. For example, for phosphorus, the sequence 1s, 2s, 2p, 3s, 3p with the number of electrons assigned to each orbital or set of orbitals sharing the same label placed as a superscript. For example, hydrogen has 1 electron in the s orbital of the first shell, so its electronic configuration is written as 1s1. Lithium has 2 electrons in the 1s subshell and 1 in the higher energy 2s subshell, so its configuration is written as 1s2, 2s1. Phosphorus atomic number 15 is as follows: 1s2, 2s2, 2p6, 3s2, 3p3. For atoms with many electrons, this notation can become lengthy, and so an abbreviated notation is used, since all but the last few subshells are identical to those of one or another of the noble gases. Phosphorus, for instance, differs from neon, which is 1s2, 2s2, 2p6 only by the presence of a third shell. Thus, the electron configuration of neon is pulled out and phosphorus is written as follows: neon 3s2, 3p3. This convention is useful as it is the electrons in the outermost shell that most determine the chemistry of the element. For a given configuration, the order of writing the orbitals is not completely fixed, since only the orbital occupancies have physical significance. The energy associated to an electron is that of its orbital. The energy of a configuration is often approximated as the sum of the energy of each electron, neglecting the electron-electron interactions. The configuration that corresponds to the lowest electronic energy is called the ground state. Any other configuration is an excited state. As an example, the ground state configuration of the sodium atom is 1s2, 2s2, 2p6, 3s, as deduced from the above principle. The first excited state is obtained by promoting a 3s electron to the 3p orbital to obtain the 1s2, 2s2, 2p6, 3p configuration, abbreviated as the 3p level. Atoms can move from one configuration to another by absorbing or emitting energy. Now, coming to the applications. The most widespread application of electron configuration is in the rationalization of chemical properties in both inorganic and organic chemistry. In effect, electron configurations, along with some simplified form of molecular orbital theory, have become the modern equivalent of the valence concept, describing the number and type of chemical bonds that an atom can be expected to form. Not all methods in calculational chemistry rely on electron configuration. Density functional theory is an important example of a method that discards the model. For atoms or molecules with more than one electron, the motion of electrons are correlated and such a picture is no longer exact. A very large number of electronic configurations are needed to exactly describe any multi-electron system, and no energy can be associated with one single configuration. However, the electronic wave function is usually dominated by a very small number of configurations, and therefore, the notion of electronic configuration remains essential for multi-electron systems. A fundamental application of electron configurations is in the interpretation of atomic spectra. In this case, it is necessary to supplement the electron configuration with one or more term symbols which describe the different energy levels available to an atom. Now, at last, let us discuss the stability of half-filled and completely filled orbitals. Above section discussed how the electrons fill the lowest energy orbitals first and then move up to higher energy orbitals only after the lower energy orbitals are full. However, there is a problem with this rule. Certainly, 1s orbitals should be filled before 2s orbitals because the 1s orbitals have a lower value of n and thus a lower energy. What about the three different 2p orbitals? In what order should they be filled? The answer to this question involves Hund's rule. Hund's rule states that every orbital in a sublevel is singly occupied before any orbital is doubly occupied. All of the electrons in singly occupied orbitals have the same spin to maximize total spin. When assigning electrons to orbitals, an electron first seeks to fill all the orbitals with similar energy, also referred to as degenerate orbitals, before pairing with another electron in a half-filled orbital. Atoms at ground states tend to have as many unpaired electrons as possible. In visualizing this process, consider how electrons exhibit the same behavior as the same poles on a magnet would if they come into contact. As the negatively charged electrons fill orbitals, they first try to get as far as possible from each other before having to pair up. Consider the electron configuration for carbon atoms 1s2, 2s2, 2p2. The two 2s electrons will occupy the same orbital, whereas the two 2p electrons will be in different orbitals and aligned in the same direction in accordance with the Hund's rule. Consider also the electron configuration of oxygen. Oxygen has 8 electrons. The electron configuration can be written as 1s2, 2s2, 2p4. The first two electrons will pair up in the 1s orbital. The next two electrons will pair up in the 2s orbital. That leaves 4 electrons which must be placed in the 2p orbitals. According to the Hund's rule, all orbitals will be singly occupied before any is doubly occupied. Therefore, 2p orbital get 1 electron and 1 will have 2 electrons. Hund's rule also stipulates that all of the unpaired electrons must have the same spin. In keeping with convention, the unpaired electrons are drawn as spin up. When atoms come into contact with one another, it is the outermost electrons of these atoms or valence shell that will interact first. An atom is least stable and therefore most reactive when its valence shell is not full. The valence electrons are largely responsible for an element's chemical behavior. Elements that have the same number of valence electrons often have similar chemical properties. Electron configurations can also predict stability. An atom is more stable and therefore unreactive when all its orbitals are full. The most stable configurations are the ones that have full energy levels. These configurations occur in the noble gases. The noble gases are very stable elements that do not react easily with any other elements. Electron configurations can assist in making predictions about the ways in which certain elements will react and the chemical compounds or molecules that different elements will form. In nutshell, it can be said that the exactly half-filled and fully filled orbitals have greater stability than other configurations. The reason for their stability are symmetry and exchange energy. First is the symmetry. The half-filled and fully filled orbitals are more symmetrical than any other configuration and symmetry leads to greater stability. Number second is the exchange energy. The electrons present in the different orbitals of the same subshell can exchange their positions. Each such exchange leads to the decrease in energy known as exchange energy. Greater the number of exchanges, greater the exchange energy, and hence greater the stability. As the number of exchanges that take place in the half-filled and fully filled orbitals is maximum, thus exchange energy is maximum and hence maximum stability. That is all about today's lecture. Hope you have understood it very well. Thank you very much and goodbye.